Today we're going to be solving the 1D heat equation with zero temperature boundaries. So this is our first day we're actually going to solve the heat equation fully. Okay, so we're going to do it for this particular example of zero temperature boundaries. Okay, so what do we mean by that? So let's write down again the heat equation. Let's, I'll just do this, use a lighter stroke there. So there's the heat equation. Now we're going to consider this constant. And that's going to be that thermal diffusivity. And we're going to do this for a metal rod. We can think of it as a solid metal rod with boundaries at x equals 0 and L. So this is the x space. We have boundary conditions u x equals 0 for all time equals 0, and u at x equals L for all time. Okay, so the boundaries are going to be 0. So we're going to have 0 out here for our giant heat bath, and also 0 out here on that heat bath, right? And then final thing is we have so that's our boundary conditions. And then we also have an initial condition. T equals 0 is going to be equal f of x. All right, so we're going to just assume that this is a given in the problem. And that's going to be our initial condition. Okay, so what do we mean given in the problem? We mean that it's just some initial temperature profile, so you could think of something like this. That's our f of x. All right, so it might be a little hotter here, a little colder there, a little hotter, a little hotter, a little colder, and so on and so forth. Okay, so we want to see how heat flows through this bar over time. So again, our goal is a solution function u of x comma t. And if I were to plot this, right, this is going to be this will make a surface. All right, so if that's our 0 to our L, and that's our x space, right? That's x. And then we can think of time as going forward like that. If this is our f of x right there, and that's at time equals 0 here. And we want to know what happens. So the surface, u x comma t, is going to be some surface that kind of goes like this out. Whatever happens to it, we don't know yet. We'll find out. But the idea is going to create some sort of surface. But it's subject to a few things. One, right at the boundary, u will always be 0. So here, u is going to be equal to 0. And on the back side there, at x equals L, u is also 0. And then here, u, x, and time equals 0, it's equal to f of x, right? And that's this function here. So that's where the boundaries come in. So if we think of u as a surface, we see we have this boundary specified. It's kind of pinned down, like carpet to the floor on the edges. And then we also have this function over here that specifies that outer edge of our boundary. Okay, we want to know what happens as time goes forward. What happens to this surface? So that's the form that this solution is going to take. All right, so those are some important concepts to have. And again, the ingredients to a PDE problem are the following three things. We have, one, the actual PDE equation. We have boundary conditions and initial conditions. And we need all three of those ingredients in order to specify a solution. So now let's go, before we start solving, we need to do a little bit more work. So some more housekeeping. And we have to make a few points about what we're going to be doing. One of the things is going to be a mathematical thing, and the other two are going to be more physical oriented. Okay, so first of all, let's write down what our heat equation looks like again. Our heat equation is going to be of the form I'm going to rewrite it a bit as the partial of u with respect to t minus k, the second partial of u with respect to x, equal to 0. All right, I'm going to rewrite this a little bit further and actually write it as a linear operator, LU, which I'm going to just put it like this: is the partial of u with respect to t minus the partial times minus k, the second partial with respect to x. And we'll put that in a big parenthetical and put the u on the outside. So again, we distribute in to get that. So we can think of this part right here as being L, and then that's our input. All right, so, and we're going to set this equal to 0, and of course this, as we remember from our ordinary differential equations class, is a homogeneous problem. And it truly is that L, for the heat equation, I can actually put down HE. We can call it HE if you want. The linear operator for the heat equation is linear. And why is it linear? What makes it linear is if U and W are solutions, i.e. LU is equal to 0 and LW is equal to 0, then C1 U1 plus C2 W is also a solution. So we can see this, and what? So that means that L of C1 U plus C2 W is going to be equal to L of U plus C2 L of W. And because that's 0 and that's 0, that's 0 plus 0, which is equal to 0. So there we go. And that's certainly true for this operator because any derivative is linear, and even second derivatives are also linear. We're just taking the difference of these two. So that's clearly a linear operator. Now, what about the non-homogeneous case? Well, then we have something like this. L of U is equal to, and the way it's written in the book is Q of x comma t over our specific heat times our mass density. And what this represents is some thermal source or sink, depending on what you want to model here. And that just represents some sort of internally generated heat inside this bar at every point x. So that could be some function of time and space of heat being pumped into the system from outside. See, so we can think of that as maybe a chemical reaction. That goes on inside the medium, or it could be a lot of things. We could actually just pipe heat in from some outside source to each point x. Something like that. So those are just some examples. But we're not going to be covering the non-homogeneous case. We'll just be covering the homogeneous case. So for today, we're just going to set that equal to 0. We'll solve the homogeneous first. All right. So that's one. So that's kind of our first little housekeeping thing, is to understand linear equations. So again, what do we mean by the solution here? So it's a solution when it satisfies this PDE, i.e. it's equal to 0. But it has to also satisfy the boundaries. Does this linear combination satisfy the boundaries? Well, it certainly does. If U is 0 on the boundaries and W is 0 on the boundaries, well then certainly the linear combination will also be 0 on the boundaries. So when I mean it's a solution, it has to both satisfy this partial differential equation here, but it also has to satisfy the boundary conditions as well. All right. So those are two things that we need to be able to do. Okay. So there's a lot of details here, and we have to sort of break it off into pieces. So right now we're just going to consider the standard zero temperature boundary condition. All right, so another point of housekeeping. This is more of the physical questions. So physical realism. So we have to question the physical realism of what we're doing, and recall that that the heat flux, and we called it phi of x, comma t. It was going to be simply the negative derivative in space of u times this thermal conductivity. So that's a constant. So we chose this, or we use this as a model for heat transfer. It may not be true all the time, and particularly let's consider critically now. Well, what do we mean by zero temperature boundaries? I'm going to put a question mark on that. Do we mean 0 Celsius, or 0 Fahrenheit, or 0 Kelvin? Those are, of course, vastly different temperatures. So what do we mean? 0 Kelvin, of course, is impossible. That's impossible. So what do we mean by this? So it turns out that we need to just put this into perspective a bit. So if U solves the heat equation, He equals 0, and U on the boundaries is equal to 0, does it mean 0 Kelvin or 0 Fahrenheit or 0? Well, it doesn't really matter. In fact, 0 is arbitrary. Because let's say we want another boundary condition. So that's an L there, equal to, we'll just call it, call it temperature T. So that, of course, is just some other temperature, maybe that's not 0. Well, so I'm going to call that solution W. That'll be the solution for this temperature. Well, I can set W then, x comma t, can just be U for the 0 boundary condition, x comma t, plus t. And we can see that L of W is equal to L of U plus t is equal to, again, we have a linear operator, so that becomes L of U plus L of t. So L of U, of course, because it solves the equation, is 0. And because t is a constant, the derivatives take that constant and also set it to 0, so it's 0. And now we know, because U plus t is going to be equal to t on the boundaries. So we have a nice way. Once we solve the homogeneous equation with a 0 boundary, and that's completely arbitrary, all we have to do is add a constant to it to get it to be into some real-world temperature, like, say, room temperature, or maybe the outside temperature, right? So some sort of realistic temperature for whatever our physical system, whatever regime it's in. All right, another point we need to make. What's the difference between, what about this bar? We have, so this is a steel bar, and let's say we have it at 0 temperature, but really we could model it any temperature T, just like we said. So sorry, that'll be, it's L out there, and it's 0 degrees, and 0 degrees here, and that's equal to L there, or X, that's equal to X there. That's X equals L there. All right, so it's 0 degrees on each end, but we can always just shift upwards. But we have some function, that initial temperature, like that. That's f of x. All right, so what do we else do we need to know? Do we expect, so what if, does it make a difference if the initial temperature is at somewhere around 1 degree Celsius? Or how about 2000 degrees Celsius? Does that make sense? What if we have a function that goes up and down between 1 degree and 2000? Is this okay? Well, clearly something's going to be totally wrong here. This defies our mathematical model, because we know at 2000 that's above the melting point of steel. So the steel will be liquid, right? That'll be liquid steel. So we wouldn't expect Fourier's law for heat flux to hold the same and with vastly different temperatures, right? So we expect that this is the material property. So the heat conductance should depend, that is only valid in some temperature regime. So if we have a change of phase from solid to liquid, we wouldn't expect that Fourier's law is going to be valid over both of those different phases at the same point. So we need to, it's just from a real world perspective, whatever our K constant is, our thermal conductivity, it's really only valid for some range. We got to make sure that when we're doing our modeling that we're not violating any physical rules about phase changes for our material. But again, these are just bigger issue questions that go beyond the heat equation. The heat equation, of course, it's agnostic of all these things. It doesn't consider the physical reality. It will compute it's valid for any numbers that you give it, but we have to just keep in mind that when we're modeling the physical system, Fourier's law is just an approximation. And it may be valid for a narrow temperature range that we want to model. So with those points in mind, now let's actually get down to actually solving. So now we're going to solve. So what we're going to do then, we're going to write down our equation again. So I'll write down it's the partial of u with respect to t is equal to k partial, the second partial with respect to x. Okay, and again we want on x equals 0 and L, and we want u t equals 0 equals f of x, that initial condition. So those are the three ingredients of my model. So what we're going to do is a method called the method of separation of variables. So u of x of t, that's the goal, that's what we want to find. We're going to I'm going to actually say we're going to guess that it's going to be of the form p of x times q of t. All right, so just another little point here. The textbook, your textbook uses phi of x, and q of x they use g of t. I didn't like this notation in the book because in a previous section we used this for the flux. We use phi for the flux, and I don't want to confuse anyone, so I'm going to use p and q instead. And that just seems to be a nice choice for letters anyway. So follow along, and but just note that the book uses different letters, but the method of solution is exactly the same. So we're going to guess that this is a product of two 1D or single variable functions. So what we always do for this is substitute. So we're going to put it into the equation. So again, we're going to have our linear operator, and we're going to evaluate it at u, which is going to be L, which we're going to now call P and Q. We're going to multiply them. And that is the partial with respect to t minus k second partial with respect to x, PQ. And that becomes, now remember, P is a function of x, Q is a function of t. So the partial with respect to t, it actually becomes a non-partial derivative with respect to q. There, and minus, and then the q comes out front. And then we have the second regular derivative of p with respect to x. Okay, and that's all equal to 0, right? We want to. So now we have this equation here. So this is where we do the separation. We're going to separate p and q's. So what we do is we separate by subtracting across or adding across. So that's q is equal to k, q second partial with respect to x of p. And now I'm going to divide through by a few things. We're going to say that's 1 over k times q dq dt is equal to 1 over p dp dx, the second derivative of x of p. All right. So now we see here this is a function. So I should say a function. I should say an equation only of t, and this is only of x. All right, so now we have on this side something that's only a function of t, and here this is something only of a function of x, and that they're equal to each other. All right, so if two functions of two different variables are equal to each other, what do they have to be equal to? Well, they have to be a constant. It's the only way two functions of different variables can be equal. And that constant could be 0, it could be positive, it could be negative. We don't know. But what we're going to do is, and this is just a notational gimmick that we always do for these equations, we're going to make it equal to negative lambda, where that right now, lambda is unknown. All right, so our goal is to find that. And why do we put that negative sign? Well, it's just a convention. And we'll see why it's convenient to use a negative there. Clearly, I could make this positive, and I just have to switch the signs and everything in my analysis. But it's no big deal. But we're going to keep with that convention because it does kind of simplify our notation a bit. All right, so here's the big leap forward: is we take this p and q, we postulate that our solution is going to be a product of these two univariate functions, and we get this neat relationship where we find ways that we can separate out the p and q from each other and set them equal to a constant. So let's write down what to do next. So again, we are going to write k over q. Now I'm going to say that that's q prime now, and that's of time. This is the time side. And here I'm going to say that's 1 over p double prime, where now this is the x side. And we're going to set that equal to negative lambda. All right, so what we need to do then is solve, we need to solve the x side, which I'll now rewrite as this right here. I'll write it as p double prime is equal to negative lambda p, or rather, we can also write it down as p double prime plus lambda p is equal to 0. Okay? So recall then that, remember, u of x comma t is equal to q of t p of x. So remember the boundary conditions, that u has to be equal to 0 at x equals 0 and L, right? So on this x side, we also require then that p be equal to 0 on x equals 0 and L as well. That's how we encode the information of the boundary conditions of u, by having those be a condition for the solution of R. And remember, this is an ODE. We have no time here. This is only of x's. So what we see, what the separation of variables technique has bought us, is a way to take a PDE and turn it into two ODEs. So we're solving that first ODE. But notice that we don't have an initial condition, we just have boundary conditions. So we have conditions for x at two different x values, or conditions for p's at two different x values. So what is the solution of this equation? What kind of functions have it so that the function's second derivative is equal to the negative of itself times some constant lambda? Again, lambda is unknown. So we got to find out what that is. But we do know that equations of this form have solutions like as follows. They have conditions like this. C1, this is going to be sines and cosines. This is going to be cosine square root of lambda x plus C2 sine square root of lambda x. So you might want to take yourself through why that's true, but this is something in your previous class, in your class on ODEs, that you probably solved many, many times, this sort of equation. All right, so but now we have to ask about boundary conditions. We know that P of 0 is equal to 0. Well, if I evaluate x equals 0 into cosine, right now this is going to be C1. And if I put x equals 0 into sine, that goes away. So P of 0 equals C1. So that means C1 is equal to 0. Okay, so that implies then that P of x is equal to C2 sine square root of lambda x. Again, this is true for any lambda that this will be happening. But we still don't know what lambda is, but we certainly know now that C2 that C1 is 0. All right, so the next thing we need to do is then put in L, and that's also going to be equal to 0. And that's going to be equal to C2 sine square root of lambda x. So, or sorry, L. We're putting L in there. All right, so sine is 0 at many places, and that implies then that square root of lambda times L is equal to, well, pi would be 1, but actually any multiple of pi, it's going to be equal to n pi, right? And that's for n is equal to 1, 2, 3, all the way up to infinity. So there's infinitely many ways we can solve this equation. And that implies, of course, that lambda is going to be equal to n pi over L quantity squared. And that is that's what we call the eigenvalue. But the square root of lambda, that's equal to n pi over L. We can think that, of course, is the spatial frequency. Right, and that's a consequence of the fact that this is all in the x side of our analysis. Okay, so now we have a solution. We have a bunch of values for lambda that work. Okay, so now what we have then is I'm going to call it Pn, or as our family of solutions of the form sine n pi L of x. And each one of those solves this equation here, this ODE. Either one of these. Okay? And it also has the property that it always satisfies the 0 boundary conditions. And we could see a few examples of this. I'll just plot a few here. Right, so the first one for n is equal to 1, we have this big, goes across like that, and it's 0 at L. And then there's another one, and that's n equals 2. And then n equals 3 kind of goes like this. That's n equals 3. And we could keep doing this. Like that, and that's n is equal to 4. And so on and so forth. We keep getting, again, that spatial frequency keeps going up, right? Every time we go up in n, the function gets a little bit more wiggly. It gets more high frequency. It has more oscillations in it. Okay, so there's a whole family of p of n's that solve this. So now let's go talk about the other side. So let's talk about the t side. So we had that equation was q prime over k over kq was equal to negative lambda. So that becomes q prime is equal to negative k lambda q. All right, so this is a first order equation that's linear, and we know that the solutions then, again from our standard ODE class analysis that we've done probably many times, q is going to be an exponential. Q of t is going to be some family of exponentials, a e to the negative k lambda t. Of course, we know what lambda is, and we know what k is. K was a given parameter in our problem, so that represents a e to the negative k n pi over L, all quantity squared. Because that's what lambda is, times t. All right, so we can actually call this Qn, and we don't really need to put the a on there. So our Qn then is just going to be e to the negative k n pi over L, quantity squared, t. All right, so put it together. We have u of n, x comma t, is going to be equal to p of n of x times q of n of t, and that's going to be, we can write it down as sine n pi over L times x e to the negative k n pi over L quantity squared t. All right, so this is a whole family of functions. So this is a whole set of functions un of x comma t, and I'll put little brackets around it. N is equal to 1 all the way to infinity. All right, so that's our set of functions, and each one of them solves. Each one of them is a solution. The ODE, or they solve the PDE with the boundary conditions. But what about initial conditions? So these functions here, this set, and it solves the BCs, the boundary conditions. But what about the initial conditions? Certainly, if let's set, so un of x comma t equals 0, that's going to be equal to simply sine n pi over L x, which is simply what we call Pn of x. All right, so if f of x, remember f of x was given to us in the problem, f of x may not be a sine wave. If f of n is not a sine wave, what do we do? Are we out of luck? So, I mean, clearly these are nice solutions. If our initial condition is one of these sine waves, then we're fine, right? We have a nice solution for it. But what if f is some other function? Like I said, we wrote that thing down there. Could be some irregular, that's 0, that's L. Some irregular function like that. This is not just a single sine wave. This is a very complex thing. What do? Well, recall we can always do some sort of approximation. Okay, so let's analyze this set of functions and see if we can come up with something about it. So what we're going to use is our linear algebra and our inner product. So I need another sheet. So again, we have p of n of x is equal to sine n pi over L of x. All right, so that's our set of functions. But now we're going to recall from the previous lectures the inner product. And we'll say that it's f comma g is equal to 0 to L f of x g of x. The inner product was that nice function, or is that nice function that's an inner product on a function space. So provided this integral exists, we can integrate f and g and their products. Then over this interval is 0 to L. And then we have a notion of angle. We have and we have what we learned was that the inner product allows us to make orthogonal projections. So what do we mean by orthogonal projections? Remember that if I had some function f of x, and I want to approximate by a linear combination of p of n's of x, and it's a set n equals 1 to some finite value of n, right? So here we have an infinite set. But let's just, for now, make this set finite. We'll say we're only going to go to a certain point. We don't want those functions that are really, really, really squiggly, really high spatial frequency functions. We're just going to take all the lower spatial frequency functions. So we're going to have a cutoff, right? So what we mean is we want to find an approximation, C1, P1 plus C2, P2 plus C3, P3, dot, 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 all the way to Cn, Pn, capital N. All right, so we know that if we can minimize the difference, or the distance, f minus this linear combination, and I'll write it as this. I'm going to call it f hat of x. And I can also call it the sum ci pi, I equals 1 all the way to capital N. Okay? F hat. And this is our estimate, or our approximation. Okay? We can minimize that distance by taking the orthogonal projections. Ci is equal to the inner product of f with pi over pi inner product with itself. Okay, so we can always then find a good approximation for any finite set. Okay. The question then remains is, what happens when capital N goes to infinity? And does our approximation, does it get better and better and better? That is, can we say that our f hat, which is going to be equal to now the infinite sum, will that truly equal f of x? So this is a question I'll leave for another day, whether we can get better and better approximations if we get more and more terms in this series. So obviously there are questions of convergence. There are lots of questions dealing with these types of approximations, but we'll leave that for another day. But assume that we can always find some approximation. Given a finite set of these functions, we should be able to find some approximation, and that certainly will be good in practice. I know if we were going to do a computer, we'd have to find some cutoff. We can't ask the computer to do an infinite sum for us. But we want to do some approximation. We have a way to do that using our orthogonal projections. All right, but this all rests on an assumption. We're assuming here that the PI's, are they orthogonal? Well, it turns out yes, they are. And that will leave for a homework problem or maybe a lab problem for you to check that these functions, that sines are orthogonal. It turns out they are. Okay, so now I'm going to leave by doing one example. A simple example then to study what's happening, what physically is happening here. So let's now say that f of x, our initial condition, is going to be equal to sine pi over L of x. All right, that's our initial condition. And again, we have initial boundaries. So that means our solution is simply going to be u of x comma t is equal to sine pi over L x times e, and so this corresponds to that n equals, that equals 1 eigenfunction, and that's going to be negative k pi over L quantity squared t. And again, this corresponds to the n equals 1 un u1. That's what this represents. That's what our solution is right there. All right, so what does this look like? So sine pi over L of x, that looks like this. I'll draw it here, 0 to L, and it goes up like that, and it just goes back down. All right, so that's sine pi over L of x. All right, now we want to go forward in time though, so I'll put time this way. Put my other boundary here. We just want to draw what this looks like. And we see here, if we just analyze this solution, this is a decaying exponential. K, of course, was a positive constant. We'll just set it equal to 1 for now. It doesn't really, and we can even set L to 1. It doesn't matter. But the idea is, as long as that's a positive constant, because of that negative sign there, this is going to be a decaying exponential. So if I fix a value of x right there, and if I look at time going forward, I know I'm going to get some decaying value. It's going to go like that. If I look at this value of x, it's also going to decay down to 0. And that's going to decay down to 0 as well. So if we see, it looks like our hump, if this sort of hump shape like this goes like that, the hump is just going to get smaller and smaller and smaller. It's going to get lower and lower amplitude till effectively, as we go out further and further in time, as we go forward in time, it's just going to be U is basically 0 everywhere. And does that make sense from a kind of a real world standpoint? Here we're saying that that's a greater than 0 function. We say it's 0 on the inputs. Remember, heat is being conducted out through the endpoints. This is like having a warm building that's surrounded by a cold winter, and we have conduction that happens on the ends of this building. So think of it as two doors open on the front and back of your house, right? So heat is going to be escaping through those openings in our building, and so you expect that the heat in the middle of the house will stick around the longest. But if you're right by a door, you expect that the decay it'll drop down to 0 a little faster. But if you're in the middle of the building or in the middle of that long hallway, it's going to it'll decay slower. All right, so that's to give you a real world perspective on this sort of thing. So again, we have a few unanswered questions about how to solve these PDEs, but we see that there's a nice way now to do it using separation of variables. So thanks.